Okay. Then I'm going to go ahead and pull up my screen share here so that I have our list. We only have 10 people back so far, so we'll have to wait a little bit for everybody. But there we have you. Screen share. Okay, there we go. Oh, and again, the Zoom chat room is open, so you can go ahead and type questions in there. But we're back here at 12:50. So what I have figured out is that you can't see me move my hands while I'm screen sharing. However, it does show up on the video. So if you saw me moving my hands on the video, you'll see that it does there. It's a little small and on the side, but I'll try to be animated. Okay. So we're going to continue on with our chapter 12, Aldehydes and Ketones, with the primary feature being, of course, that ketone or that carbonyl group. That ketone/carbonyl group is really one of the best group. It has a lot of features to it, and so what we're going to look at is one of the weird features it has is what we call eno-keto tautomerism. Okay, so basically the idea is that tautomers are two different resonance forms that one will definitely be favored over the other. However, that there is a difference in energy and a different reactivity between the two. So in the case of the enol-keto tautomerism, we have a ketone, which is the keto form, and then we have the enol form. And so if you think about it, an alkene with an alcohol on it is an enol, right? So when we look at these features here, we see that our, let's go blue here, in our ketone form right here, we have just the carbonyl compound. Come on, there we go. So we have just this carbonyl right here, which means that this side is partially positive and this side is partially negative here, and that's going to control its reactivity, okay? But if we took a hydrogen from up here and moved it up to that more electronegative oxygen here, what we'll end up with is the other form of this. The other form of this, which I will circle in red now. Come on, start sharing. There we go. All right. So notice we have an alkene and an alcohol, okay? So because we have an alkene and an alcohol on this group, it will not react the same as the ketone. The ketone has that partially positive and partially negative side. Now we have something that can hydrogen bond and something can add across an alkene, okay? So what does that mean for us in reactivity? It means that even though we have a ketone, sometimes it's going to react like an alkene with an alcohol on it. And even if we have the alkene with an alcohol on it, sometimes it's going to react as a ketone. So we have to figure out which form predominates most of the time. Okay, and so what I'm going to do here is, if it'll let me blow this up here, okay. So it varies with the amount of the conjugation, and it varies with the stability of the alcohol formed, okay. So if we think about a nice small compound like this, let's see, that's 2 carbons, so that's going to be ethyl, and it's an aldehyde, so it'd be ethanal. So in ethanal, if it had it in the keto form, it would have that aldehyde in place. Here it would be hydroxyethylene, okay? Now, what does it mean, the percent of enol in equilibrium, okay? What that means is, well, there's not very much here. For every 10,000 of these, right, of the aldehydes, we only have one of them being the enol form, okay? So that's not very much, okay? So most of the time we probably wouldn't have seen it, okay? But something about its reactivity tells us that it does exist, okay? So let's look at the next one here. And this is acetone. This is our simplest ketone right here. It's only got 2 carbons on there, but when it has its equilibrium here, again, it's about almost 100,000 to 1, where for every one of these, you have 100,000 of these, meaning it's much more stable as the ketone than as the Enol, okay? So, but we still know it exists because the way it reacts. And we get the same kind of shifts in the cyclohexanone and the cyclopropanone here, where it's actually, notice the cyclohexane is actually more common than the other forms right here. So there must be something about that reactivity there. This number's lower, and therefore it's a little bit more of these than in comparison with these up here. But so the idea here is that while it's not happening very much, when it does happen, it changes the reactivity. Okay. So let's draw some of these as enol and ketones just to see how they exist and why they exist, okay? So the idea in all of these is that you have one hydrogen is going to move from our group that's next to the carbonyl to the oxygen of the carbonyl. So if we were to draw the enol of this particular compound here, what we're going to do is we're going to not break any carbon-carbon bonds or carbon-oxygen bonds, okay? But we are going to move a hydrogen from one of these up to the next one here. Okay, now, we could move it from this side and give us this alkene with this and our substituent here. However, what do we know about alkenes? Okay, the more substituted the alkene is, the more stable it is. Okay, so what's really going to happen is we're not going to form this double bond here. We're actually going to form this double bond here as more stable. So our enol form of this compound here is actually going to have our double bond in the most substituted position possible. Notice there are 4 things substituting that double bond. If it was on the other side, there'd only be 3. So this is going to be the most stable form of this. But again, it's going to be shifted mostly to the ketone side of it. Sorry, that should be a single arrow, not a double arrow. It's going to be shifted mostly to the ketone. Okay, so the only thing that moves when we do our enol-keto tautomerism is one hydrogen moves from a carbon next to the carbonyl up to the oxygen. And when we do that, we want the most substituted alkene possible. So if that was true, then we're not going to make our enol with our double bond on this side here. We're going to make it with it on this side here, because that's going to be more substituted. So when we draw our enol-keto tautomerized 1, 2, 3, 4, 5, 6, so that'd be hexanone, we're going to draw the double bond on the more substituted side, and we're going to move our hydrogen up to our oxygen here. So these are the 2 forms, the keto form, which has the ketone in it, and the enol form, the one that has the alkene and the alcohol form. And again, we're going to form it where it forms on the more substituted side. Okay, and we're going to see that the way it reacts. And that's why I wanted to draw attention to it right now. All right, so we can also go the other way, go backwards, and try to figure out where to put take the alkene away and add an alcohol. Are the more substituted carbons usually toward the middle of the molecule? In general, yes, because that is where you have more connections. For example, over here, because it's over here, it has 3 hydrogens on it, and it's toward the outside of the molecule, it has fewer carbons attached to it. Yes, in general, the more substituted is toward the middle of the molecule or the internal portion of the molecule. Okay, that was a question in the text, the chat box, by the way. Okay, so if we redraw this one right here to show you that the OH is up here, it makes it easier to show you where that enol-keto would be, which means the carbonyl is going to end up on this bond, and this is going to turn into a single bond. So if we're going to draw the other isomer of this, we would keep the same carbon-carbon ring structure. This ketone doesn't change over here, but we end up with a carbonyl here. And because that carbonyl has a hydrogen on it, it makes this side an aldehyde. Okay? So by looking at this, again, this is the enol form, this is the keto form. It's going to shift mostly to the ketone side. However, we know that the oxygen with the OH on it becomes the carbonyl, okay? We don't want to break any sigma bonds. All we're doing is moving that pi bond from between the carbon-carbon and the carbon-oxygen, and we move one hydrogen only, okay? That's the key. It's not a resonance form, right? Because we've actually moved up an atom here, but we don't break any sigma bonds. All we do is change where that hydrogen is attached and where the double bond is, where the pi bond is. Okay, so if we drew one more, oh, this would be an interesting one here. So we can do this also. I'll let you do this one by yourself. Let me do this one here, because this one's kind of interesting. Okay, so again, we're not going to break any of these carbon-carbon bonds right here, but we need to move a double bond and we need to move a hydrogen. So the only option we have for us on this one here is to keep most of the structure the same, and we end up forming a double bond between the oxygen and the carbon, and the hydrogen gets transferred over to here. So this is the enol form right there, and this is the keto form right here. Again, it's not a resonance structure. We're actually moving a hydrogen, and we're moving the location of the double bond. We're moving it from between two carbons to between the carbon and the oxygen. Okay. So that being said, and being that the ketone is the more stable, why is it important we understand? Okay. It's very important to understand because under conditions where we can protonate our ketone, like in the presence of any acid, or sometimes water is enough to do it, we can change the reactivity of acetone or a ketone. And the way it works is the first thing we do is we do what we do in a lot of different mechanisms. If we have an acid present, we're going to add a proton, okay? So on the molecule here, oxygen is the most electronegative atom, and so when we added a proton to there, this oxygen is acting as our Lewis base, and therefore when it accepts the proton, we end up with our protonated species here, okay? So technically, this is our conjugate acid because it acted as a base, it took a hydrogen, okay? Once it takes that, it now is more acidic than it was before, and it can do two things. It can lose a proton to what is now the base, and in this case, notice this right here became the base, right? So the part of our acid that was attached to the proton now becomes our base. Now, that base can take a proton from two different locations. It can take the proton back that it just gave, or in the case of forming the enol, it actually removes the proton from the carbon next to the carbonyl, not from the oxygen. If it takes it from the carbon next to the carbonyl, that's going to kick these electrons in and give us the enol form and give us back our neutral species. Notice we started with a neutral species up here. We protonated our species. We created a base, and then we used that base to turn it back into a neutral species. Okay. This is how it forms, specifically in the case of acidic materials. Okay. Okay. So one of the reasons we know this happens is because we can actually see a racemization or making a mixture of R and S compounds by adding an acid catalyst. Okay. So if we took this pure compound right here and kept it in the absence of acid, we could isolate that compound and say, okay, this part of the molecule is our 3-phenyl-2-butanone, because we have a methyl group, a ketone, a hydrogen, and a phenyl group here. So we can actually isolate it and say it's exactly this compound. However, if we put it into a solution where it has even a trace of acid or base, what happens is we go from a pure optical material that is only R to a mixture, a 50-50 mixture of R and S. And the reason it does this is the fact that it goes through that intermediate right here, our Enol intermediate. We take our sp3 hybridized carbon here, turn it into an sp2 hybridized carbon, and then when the hydrogen goes back, it changes that carbon back into an sp3 hybridized carbon. Okay, because this compound is trigonal planar, that proton can come in from the top or the bottom. There's no specificity. Because it can come in from the top or the bottom of this planar structure, this is trigonal planar, okay, means it can come in from the top. If it comes in from the top, it forms one isomer. Comes in from the bottom, it forms the other isomer. Okay, so this is one of the first examples on how we knew this keto tautomerism happens. And by measuring how fast the optical activity goes away, we can see how little or much of the enol form is actually there. And that's where we get those ratios that we saw over here in the shift of which way it's shifted, because we can measure the speed at which these change. Okay, so that's one of the reasons we see it happens. And now let's take advantage of it by doing reactions with it, okay? And the one reaction that I think really shows what's happening here is what we call alpha halogenation, okay? So in alpha halogenation, we see that we can get our bromine here to react with a compound that it has no functional group, right? There's no double bond for it to add to. The benzene won't react with it unless it has a Lewis acid catalyst. We learned that in last week, that you have to have iron bromide or iron chloride to make it react with the benzene ring. So in theory, bromine shouldn't react with this compound at all. However, in the presence of a little bit of acid, in this case acetic acid here, okay, what happens is it goes between the eno and the keto, and the bromine reacts with the enol form, okay? Let me show you that mechanism step by step, just to make sure we have our idea here. So again, the bromine is not going to react with the ketone at all, okay? There's no double bond, there's nothing for it to react with here, okay? Come on, stop mirroring, remirror. My iPad's being temperamental today. All right, let's see this. Yeah, there we go. All right, so what we see here is that the bromine's not going to react with the keto form. But once it forms the enol form, we now have a double bond. And we know we can add bromine across that double bond really easily, okay? And we can do that a couple different ways, okay? So the first thing we have happen here is once we form the enol right here, the electrons from the double bond can reach out and grab the bromine, just like they did before when we had the other reaction of adding a bromine across alkene. However, when that happens, we now have the lone pair from the oxygen come down and reform our carbonyl and give us this charged species here, okay? So instead of adding it across the double bond, what happens is the electrons reach out and grab half of the bromine molecule, giving us the bromine minus, and then the electrons come back in and stabilize it in this protonated ketone form, okay? So what do we know about our protonated ketone form? We're going to have this act as our base and remove the proton from our protonated ketone form to give us our product. Okay, so again, we know this happens because the bromine would not react with the ketone by itself. The fact that the bromine reacts specifically on the carbon next to that carbonyl tells us we're forming this enol in even a small amount. It'll continuously react to give us our brominated compound. Now we can use this to our advantage to create new molecules by, once we brominate that position next to that ring, we can then go ahead and use some kind of nucleophile to do substitution at that center right next to the carbonyl. So we can generate these new compounds through our standard SN2 attack that we learned early on with our halogenated compounds to create new compounds, which we couldn't do unless we were taking advantage of this eno-keto tautomerism. Okay? So this is the first reaction that I wanted to share with you about okay, stop sharing right there. Okay, and that's one type of reaction we have with the carbonyl compounds. Okay, now I want to show you a few more kinds of reactions, and that's going to be our chapter 12 goals 3. And let me go ahead and share my screen. Okay, anybody have any questions? Go ahead and make sure you tap into the Zoom chat there. Share. All right, so now we're up to chapter 12, goal 3, the reactions of the ketones. Okay, so goal 2 is slightly separate because we're really reacting the enol, right? So that's why I separated it out to give us an idea that that is one possible reaction. Now we're going to go look at the other reactions that just involve the carbonyl. And the key with the reaction of the carbonyl is the fact that that carbonyl is partially positive. Okay, so most of the reactions we're going to talk about is having a reaction between an electrophile and a nucleophile to form a new covalent bond. Okay, so in the case of our carbonyl here, we have our partially positive, which means that a nucleophile or something with a negative charge can attack it in this configuration. And we go from this sp2 hybridized trigonal planar carbon to an sp3 hybridized tetrahedral carbon. So we're doing an addition across that double bond, meaning something ends up being attached to the oxygen at the end. Okay, usually a lot of times it's just a proton transfer, and we'll see the creation of an alcohol. Okay, so basically all we're doing is taking a nucleophile or Lewis base and attacking the partially positive carbon to create a new sigma bond. Okay, so let's look at the first reagent we want to look at here, and it's called a Grignard reagent. Okay, now this was originally created and they weren't really sure exactly how it worked, but the idea is that we can generate this nucleophile by reacting an alkyl halide right here with magnesium metal. Okay, so what's going to happen is the magnesium metal is actually going to be reduced down from magnesium 0 to magnesium +2. Okay, and that's going to generate its insertion into this bond here, which means we're going to have a carbon with a negative charge on it. The magnesium has a +2 charge in it, and the bromine having a negative charge on it. Okay, so what's the net result of this? The net result is we have a negative charge on carbon that's stabilized because of the metal, and that turns our carbon into a nucleophile. We have a negative charge on carbon. We now have a carbon nucleophile. That's the key to the Grignard reaction. All right, let's look at that in a little more specificity right here. If we look at the electronegativity difference between carbon and magnesium, it's only 1.2, okay, which means that it is a covalent bond. Remember, it has to be greater than 1.9 to be an ionic bond. So we have a covalent bond, but it's shifted where the carbon is more electronegative than the magnesium. So unlike other compounds where the carbon is partially positive, in this case, the carbon is partially negative. That partially negative carbon or a fully negative carbon is called a carbanion, okay? That's where the carbon bears the full negative charge, okay? So what does that mean for us? That means for us, we now have a way to make a carbon-carbon bond by taking a negatively charged or partially negatively charged carbon and attacking a positively charged or partially positively charged carbon. Okay, so we're now being able to create a new carbon-carbon bond. Okay, but the key feature here is that we have a partial negative charge or a negative charge on carbon, turning it into the nucleophile. Okay, so what does that mean? Okay, well, the fact that it is a partially negative charge means that it reacts actually with anything that has a slightly acidic proton. For example, it reacts with water. It'll react with alcohols. It'll react with phenols, carboxylic acids, even amines. Anything that can partially hydrogen bond or has a slightly acidic hydrogen, like even in the case of alkenes, it means it'll react. So this right here will pull a hydrogen off any of these compounds, turning it back into the regular alkane and turning all of these things into salts. What does that mean for us? It means we can't use anything that's more acidic than acetylene in our solution, or else it will react, okay? Which means we're gonna have to choose our solvent very carefully, but it also means that, oh, look, notice none of these are aldehydes or ketones. That means we can react our Grignard reagent with aldehydes and ketones. Okay, so because that'll react with all alcohols and water, we cannot use those as solvents. We'll just end up getting an alkane. It'll be an irreversible reaction. However, in the presence of carbonyl reactions, we get something really cool happen, okay? So the first thing that happens when we treat something like formaldehyde, remember that's our simplest aldehyde, it has 2 hydrogens on it, okay? What happens is our electrons from our carbanion will go and make a new sigma bond onto there and generate a negatively charged oxygen right here. And then if we quench that reaction with water or anything acidic, we'll end up getting an alcohol, okay? So anytime you have a carbonyl attacked by a Grignard reagent, you create an alcohol, okay? But can you create different kinds of alcohol? The answer is yes. If you use formaldehyde, you will get a primary alcohol because the carbonyl already had 2 hydrogens on it, and those 2 hydrogens end up as the connection on the carbon here, and only your carbanion makes the longer chain. So formaldehyde always makes primary alcohols, okay? Okay, what if you had an aldehyde that wasn't formaldehyde? Okay, that means all other aldehydes yield secondary alcohols, okay? And let me show you why, okay? So if we look at our carbonyl here, we already have 1 carbon bond to it. When we attack with our Grignard, we're going to add a second carbon bond. And the carbon left has a hydrogen on it and will have an OH on it. So all aldehydes that are not formaldehyde yield secondary alcohols. The first group being the group that was already on the aldehyde. The second group being the nucleophile you're attacking it with. Notice this is the first one right here, and here is the second one we attacked it with. And when we add acid, we end up generating a secondary alcohol. Okay, so this is important, okay? If formaldehyde yields a primary alcohol, and all other aldehydes yield a secondary alcohol, what do ketones do? Okay,
ketone already has 2 R groups on the carbonyl, and you're attacking it with a 3rd R group. So that means that I can't believe I cut that out. That if you react ketones, ketones will give you tertiary alcohols every single time. Okay? So formaldehyde gives a primary alcohol, all other aldehydes give you secondary alcohols, and all ketones give you tertiary alcohols. And I'm sorry I cut that slide out. It's on the video. You should go look at it. It'll show you that it's really nice and consistent about that. Okay, so what's the other thing we can do with aldehydes and ketones? I told you before that when they react with water, they can hydrate or be protonated by that right there. And so that means that it'll do anything that can hydrogen bond, can form a reaction with it. And in the case of water, it forms what we call a hydrate. Okay, but if you react it with a molecule containing an OH group, for example, an alcohol, you end up getting what we call a hemiacetal. So an acetal, it used to be a ketone or an aldehyde, and then it reacts to form a protonate, have an OH and an ether group on it. Okay, so look at what's happening here. The oxygen is adding to the carbonyl side, the hydrogen is adding to the oxygen side, and we get what we call a hemiacetal. Okay, so the cool thing about a hemiacetal is we can use it to protect a ketone because it no longer acts like a ketone because it's protected as the hemiacetal. Okay, now the weird thing about hemiacetals is you can actually do them within their own molecule. If you have an alcohol and an aldehyde or a ketone on the same molecule, you can actually close that ring and generate a cyclic hemiacetal. This hemiacetal now reacts like an alcohol. It does not react like a carbonyl. So that's an important thing to know when we have those groups. So it works with water to create hydrates. It works with alcohols to create hemiacetals. So, but what could you do if you remove the second OH here? Okay. Okay, actually, this is just the mechanism for the acetal formation. I'll go through it real quick for you here. So once you form the acetal, the hemiacetal right here, what you can do is you can remove that water. And the first thing we do to remove that water is we protonate the OH group. And when we do that, it creates our better leaving group here. Now, water, remember, water is one of our good leaving groups here. And now we can displace that with our electrons from our material here to regenerate our aldehyde, which then can which can resonance stabilize, giving us a cation here, which then can react with another equivalent of alcohol to give us the first equivalent of alcohol that was already on there. And then our protonated alcohol, if we lose this proton, we'll actually end up with 2 alcohols on here. Okay, so a hemiacetal is when you have 1 alcohol hooked up to it. This is what we call an acetal, which has 2 alcohols, and we've eliminated 1 entire equivalent of water to do so. Okay. Now, what that does now is it makes this a very interesting intermediate because we no longer have an alcohol, so it won't react with things that are bases. We don't have a carbonyl, so it won't react with Grignard reagents because it won't react with that. So we can actually use this to protect our ketones from certain reagents and react only one side or the other of the compound. Okay. So then we can also use this to our advantage in other ways. Instead of using an oxygen to protect our carbonyl compound or react with our carbonyl, we can actually use nitrogens as our bases, as our nucleophiles. And when we react, our lone pair on our nitrogen here comes in and interacts with our carbon here, and then we transfer both of these hydrogens to the oxygen here. We'll lose water, and we'll form a carbon-nitrogen double bond, okay? Now, it forms this in equilibrium. However, the interesting thing about this is now that we have the carbon-nitrogen bond, the carbon-nitrogen bond is less polar than the carbon-oxygen bond because the difference in the nucleophilicity between the nitrogen and the water. What this means is that makes this carbon less partially positive than it was before when it had the ketone here. So we can actually use this to change the reactivity of our ketone or aldehyde by adding an amine to it. Okay, so, but the first step in that reaction is having our nucleophile interact with our partially positive carbon. Okay, and so the mechanism is nice and simple. We have our attack by our nucleophile to generate our new carbon-nitrogen bond here. Then we have a proton transfer to give us our alcohol. Then we can have another proton transfer to the alcohol to give us our better leaving group here. Then our electrons kick in and electrons kick out to give us our new carbon-nitrogen double bond from our old carbon-oxygen double bond. Okay, so that's another thing that can happen when we have attack of a nucleophile by onto the carbonyl compound. Okay, so one of the reasons we might do this is because remember in our amine reactions, we had very few reactions that we could do. It was very hard to, excuse me, stop at our secondary amine if we just attacked it. This is one of those ways we can actually go around the fact that it's so nucleophilic by stopping it halfway through at the amine functionality and then reducing it down to get to our secondary amine. Okay, so let's talk about another reaction we can do with aldehydes and ketones. Come on, share. There we go. So the next thing we can do with our system here is, okay, we saw that when we looked at our priorities that aldehydes ranked above ketones, but carboxylic acid react above aldehydes, okay? And the reason that is that the carbonyl on a carboxylic acid, it has a higher oxidation state, and therefore slowly aldehydes will oxidize down in air until they get to carboxylic acids. But we can also speed the reaction along with a reagent called chromic acid. So anytime you have water plus chromium trioxide, you'll get this compound called chromic acid. And chromic acid will reduce all aldehydes down to carboxylic acids. And some very reactive aldehydes will even react with air to get you down to carboxylic acids as well. So aldehydes are easily oxidized down to carboxylic acids. But ketones do not react with the chromic acid because they're already oxidized down to this C double bond O. You cannot oxidize off of that carbon-carbon bond. The other way to prepare carboxylic acids from aldehydes is to use what we call a tolerance reagent, or what we do is we use a silver salt. The silver salt here will take it down to silver 0. This is silver +1. It'll take away electrons from your carbon here to give you silver metal and your carboxylic acid in the presence of water. The cool thing about this is that we, for a long time, use this as a qualitative test to prove that you had an aldehyde. Because if you mix silver nitrate in with an aldehyde, it would plate out a silver mirror on the test tube. And they used to call it the silver mirror test. And so it all has to do with going from a silver 1
gaining 2 electrons to give us silver 0, and oxidizing our aldehyde to a carboxylic acid. So we have 2 different ways of oxidizing aldehydes to carboxylic acids. All right. Well, so let's do that again. So aldehydes can be oxidized down to carboxylic acids. Ketones cannot. Okay. What if we went the other way? We went, instead of oxidizing something, we add hydrogen across that carbon-oxygen double bond. Okay. So when we do that, if we just added hydrogen across that double bond with an aldehyde, we already have 1 hydrogen on there. We're going to add a second hydrogen to the carbon and a hydrogen to the oxygen. So aldehydes will give us primary alcohols. Okay. If we did the same thing to a ketone, all ketones, when we add hydrogen across the carbon-oxygen double bond, we get to secondary alcohols. And remember, if we wanted to get to a tertiary alcohol, we would take a ketone and react it with a Grignard reagent. Okay. So if all aldehydes go to primary alcohols and all ketones go to secondary alcohols, what else do we have? Okay. So we can do this reduction in a couple different ways. We learned about reductions when we had alkenes. And when we had alkenes, we had hydrogen plus some kind of metal catalyst like platinum, palladium, or nickel. Okay. And this is true. This will react a carbonyl down to, it'll reduce that double bond down to an alcohol right here. And it'll also reduce down any alkene down to that alcohol too. But what if you wanted to be very specific and not touch the double bond and only touch the carbonyl? We have to use a slightly different reagent. Because this hydrogenation reaction right here with platinum and metals will add across any double bond, we need to find a special reagent that only adds across the carbon-oxygen double bond. We actually have that reagent here. That reagent is what we call aluminum, or called metal hydrides. Okay, so we have 2 at our disposal here. We have sodium borohydride, and that's because we have boron with 4 hydrogens on it, and then sodium is the counterbalancing ion. We can also do it with aluminum. So we call this lithium aluminum hydride because we have 4 hydrogens around that aluminum. Now, the reactive species in both of these is what we call the hydride ion. And it's basically you take your proton and you take your neutral hydrogen, and add an electron to it. That's filling its s orbital, giving you a negative charge. Okay, wait a minute. Filling our orbital, giving us a negative charge. When we have our negative charge, it acts as a nucleophile. So that hydrogen is going to specifically attack our partially positive carbon on our carbonyl. Okay, so that means that our sodium borohydride and our lithium aluminum hydride will react specifically with carbonyls to give us a specific reduction. So let's look at that in practice here. Okay, so let's say we had any old aldehyde or ketone and we reacted with sodium borohydride. For every hydrogen on this sodium borohydride, you can transfer it to one carbonyl. Okay, so we can actually end up adding 4 aldehydes to a single equivalent of sodium borohydride, giving us a compound that has 4 different carbons, 4 different oxygens bonded to boron. And then if we take that and break those bonds with water, we get a primary alcohol out in the borate salts. Okay, so what is happening is the hydrogen is acting as a nucleophile and attacking the carbonyl, giving us a negative charge on the oxygen. That negative charge on oxygen is then bound to the boron that can be hydrolyzed away using water. Okay, so if that's the step for an aldehyde to make a primary alcohol, why does a ketone make a secondary alcohol? And the reason is the same. What we have here is attack by our hydrogen as our hydride. This is our nucleophile. It attacks the carbonyl here, giving us our salt here, okay? Because we already had 2 R groups on our carbonyl, right here, that's going to turn that into a secondary alcohol when we take off the boron using water, okay? So all aldehydes will be reduced down to primary alcohols by sodium borohydride. All ketones will be reacted down to secondary alcohols because we're going to add just across the carbonyl. Okay, so that's sodium borohydride or lithium aluminum hydride. Okay, so how can we do this specifically? React a carbon-carbon double bond versus a carbon-oxygen double bond. And the key here is to make the carbonyl not act like a carbonyl if we want to reduce down just the aldehyde. If we want to reduce down just the carbon-carbon double bond. So, for example, if we have an alkene and a carbonyl on the same compound, and you use sodium borohydride, it's only going to attack the carbonyl. Okay. However, if you had both on there and you only wanted to do the double bond, you have to make the carbonyl not act like a carbonyl. The only way to do that is to turn it into, in this case, an acetal. The acetal looks like an ether. It has no carbon-oxygen double bond. Therefore, you can reduce down your carbon-carbon bond. And then by removing the acetal, you can regenerate your carbonyl. Okay. So that's kind of a cool specific reaction. But I wanted you to see that the reactivity specificity gives us abilities to look at one functional group versus the other functional group. Okay. So the key here is that when we reduce down carbonyls, we use sodium borohydride or lithium aluminum hydride. When we react carbonyls with Grignard reagents, we get primary alcohols with formaldehyde. We get secondary alcohols with aldehyde, all other aldehydes, and we have tertiary alcohols with ketones, okay? So, all right, to get a primary alcohol, we use sodium borohydride and any aldehyde. To get a secondary alcohol, we use sodium borohydride and the ketone, or, there should be a big or here, a Grignard and any other aldehyde. To get a tertiary alcohol, we can use any ketone and a Grignard reaction. To get a primary or secondary amine, you can use that reaction where we use a nitrogen nucleophile to displace the carbonyl and then reduce down. If we want to protect an aldehyde or a ketone, we use the acetal. And if we want to reduce aldehydes to carboxylic acids, we are going to use aldehydes here, and this is actually in the video. These two are in the video about different cyclic ketones can go through an Enol keto tautomerism and actually oxidize as well. All right, questions about aldehydes and ketones. The key reaction here is that your carbonyl has a partially positive carbon. Use that to your advantage to attack it with nucleophiles, okay? And when we do our reductions here, our nucleophile here is the hydride functionality, or the negatively charged nitrogen in sodium borohydride or lithium aluminum hydride. All right, I'm going to stop sharing there. Any questions for the chat before we head on out? Stop share. Okay. So go ahead and I should have all the homework posted today before the end of the day for all 4 chapters. The next chapter is carboxylic acids. So we started our carbonyls off with aldehydes and ketones. We're going to continue with carboxylic acids. The next chapter is carboxylic acid derivatives. And then we're going to end up on a very interesting topic, which is the enol anions. bonds, which is another way to use the carbonyl to create new carbon-carbon bonds. All right, any questions right now? I'm going to go ahead and stop recording and start that as saving.